Okay, good morning. Welcome to 434. Sorry, I'm not able to come for this lecture in person. I have to be at an NSF review panel tomorrow morning. So I decided to record this lecture offline. And in Wednesday's class, if there are any questions from this lecture, I'll be happy to discuss. In fact, I'll spend the first 10 minutes of Wednesday reviewing this lecture, but this lecture should give you a good understanding of the topics that I was supposed to talk about tomorrow morning. Okay, so we were talking about GPS last class, and I hope you have a reasonable understanding of what goes on. Again, that's a very deep topic. There can be multiple courses just dedicated to GPS. We just had a very high level view of how GPS signals work, how localization works. And today we are coming more into mobile computing topics, particularly Wi-Fi based indoor localization. Okay, so let's get started. GPS was extremely successful, right? I mean, even now, it's one of the de facto standards of localization. Every time you're driving, you're out in the open, in the park, you want to look up something, restaurants around you, GPS is the way to do it. Unfortunately, in indoor environments, GPS do not work. Right? Why is that? Because the GPS signals are so weak, they're coming from satellites, remember? So by the time they arrive on the roof of a building, they do not have enough power to penetrate the concrete, the roof of the building and go inside. And as a result of that, GPS signals are hard to catch from inside indoor environments. And as a result, a large section of the mobile computing research community started thinking about alternative localization solutions. And one of the attractive technologies was Wi-Fi. Okay, and so there the idea was actually very simple to start off with. People said, look, GPS is essentially a bunch of satellites, 4 satellites, which are essentially used to give me my location X, Y, Z, and in GPS's case, delta, which is your clock offset from the satellites. So why don't we do the same thing or similar stuff with Wi-Fi, where instead of satellites, now these Wi-Fi base stations that are there in our environment, why don't we use them as kind of indoor satellites and allow my mobile phone to compute its location from these Wi-Fi access points. Of course, these Wi-Fi access points belong to different owners. So this might be your neighbor, right? This might be your apartment. This is your apartment. And this might be the Starbucks next door to you, right? So these Wi-Fi access points belong to different owners, but nonetheless, the mobile phone over here, the mobile phone is able to hear all of these Wi-Fi access points, very similar to how one phone would hear multiple GPS satellites. And then the question is, why can't you do X, Y, Z localization? You don't even need to worry about delta. Can you do XYZ localization? Of course, if you can estimate clock, that's great, but you don't need to. We only care about indoor localization. Okay. So just as a quick comparison, right? GPS signals do not penetrate into buildings, right? So how about bringing GPS-like trilateration to Wi-Fi, right? So the question is, oh, by the way, I don't remember if I mentioned this, what we talked last time about GPS signals, the mobile phone receiving GPS signals and computing the distance R1, R2, and R3 from each of these satellites, and maybe even R4, from each of these 4 satellites. Computing the location from distance is called trilateration. Again, remember, we said for each of the satellites, there is a circle, and the phone essentially lies at the intersection point of the two circles, right? And this kind of uh, distance-based localization is called trilateration. Later in the course, we will look at what is called triangulation, where we look at angle-based localization, meaning from some device you have an angle theta or theta 1, from another device you have an angle theta 2, from another device you have an angle theta 3, and from those angles we can also compute where the location of the device is, and that would be called triangulation. Okay, so GPS does trilateration, and the question is, can we do trilateration with Wi-Fi as well? What are the challenges? What are the problems, right? So let's quickly look at a few of the comparison points between GPS and Wi-Fi. Okay. So one of the issues that came up when we started thinking about Wi-Fi based localization was, look, GPS signals are mostly line of sight, or which is also called LOS, line of sight, with few echoes or multipath. What does that mean? That basically means that when there's a satellite, the signal from the satellite arrives at the mobile phone mostly as a straight line, right? This is the face of the earth, and the signal arrives mostly as a straight line, and maybe one signal bounces off the road on which the mobile phone is, on which the person is carrying the mobile phone, maybe bounces off the road and maybe bounces off the person's body and arrives at the phone. And maybe the one that bounces off the body becomes pretty weak. So if you look at the power of the signal that is being received by the phone, most of the power is contained in the direct straight path, which is called a line of sight path, and only a little bit of power gets dissipated or comes from these reflections from the roads or maybe from the buildings nearby. Okay? In fact, this is the case most of the times, except maybe in a place like Manhattan, where there are lots of skyscrapers and buildings around. And in that kind of a situation, the GPS signal bounces off a lot and comes to the mobile phone. As a result of all these bouncings, this is why GPS actually suffers in performance in downtown Chicago or downtown New York, right? Because there's too much of what is called multipath or echoes in the environment. But in most places in the US and around the world, there's not that many reflections. As a result, most of the power is in line of sight. And because of that, you can exactly measure the distance very well. If there were too many echoes, then measuring that distance R1 would be problematic. I hope you see that. Okay. In contrast, in Wi-Fi, heavy echo or multipath why in indoor environments? Because there are so many walls, furniture, mirrors, TVs, the floor, the ceiling. There are too many things on which the Wi-Fi signal is actually going to bounce around. Okay, so imagine there's a ceiling, there's a wall, there's a floor, there's a furniture, there's a TV, there's a chair, table, so on, and all of these signals are bouncing before they come to the mobile phone, right? There is, of course, a line of sight path. Here there's a line of sight path, but there are all these bounces. Right? So this heavy multipath makes it difficult to figure out exactly what is the time that the signal arrived at the mobile phone. And in fact, if you now move the mobile phone, things will change. And not only that, even if the environment moves, means even if someone else is moving in the environment, the time at which the signals will arrive at the mobile phone will be different. I hope you see that. Right? So this is one major difference. Second, GPS satellites are clock synchronized. We talked about that in the last lecture, right? There's a GPS center that are synchronizing them. But in contrast, Wi-Fi access points or base stations or routers, whatever you call them, the boxes that you have at home, are not clock synchronized across different owners. Your Wi-Fi router and your neighbor's Wi-Fi router and the Starbucks' Wi-Fi router, their clocks are not necessarily synchronized, not at all, right? So trilateration, where even if you try to estimate the delta at your mobile phone, you would have different deltas from different Wi-Fi access points. That means you will not be able to have a determined or even over-determined system. The third point is that the GPS satellite locations are known. This is your ephemeris data, and the GPS centers, the ground centers, they know the satellite locations at any given point of time with very strong accuracy. In contrast, if I ask you, you might know your home's Wi-Fi location, although you have to measure it with some kind of a laser ranger or something. But if I tell you, hey, where is your neighbor's Wi-Fi access point? You cannot go and ask your neighbor, hey, my mobile phone wants to do localization. Can you please tell me the precise coordinates of your Wi-Fi access point? That's not feasible, right? So Wi-Fi AP access point locations are unknown. So these are some of the major differences. And as a result of this, it is not easy to bring trilateration to Wi-Fi. Okay? I would encourage you to kind of go home and think about it and see if there is some way you can bring trilateration to Wi-Fi, but you'll realize that these three factors actually make things quite difficult, which is not the case in GPS because, America spent a lot of millions, billions of dollars putting these satellites in space and making sure they're precisely moving and precisely monitored. With Wi-Fi kind of a ad hoc system. And the reason I say ad hoc is because your neighbor buys a Wi-Fi router and just throws it at some corner. You buy a Wi-Fi router and throw it some corner. So there's no systematic way of deploying these Wi-Fi routers. And even in this chaos, using this chaotic infrastructure, if you want to do something as precise as localization, it is not easy. You cannot apply the same kind of GPS-like algorithms into Wi-Fi. Okay? So it is at this time, it's in this context that around 1999, this is around the time when the Wi-Fi standard was being ratified, meaning many of the companies were coming together and says, okay, let's have a common Wi-Fi standard. This is how the world will actually no longer connect to Ethernet. They would be able to operate on wireless signals, and that would be Wi-Fi. So 1999 Wi-Fi standard, which is also called IEEE, the name of the standard is IEEE 802.11. The standard was being formalized, was being ratified, and all the companies were saying, yes, my chips, my Wi-Fi chips will all follow the same standard. So at this time when the standardization was happening, some researchers started thinking, why don't we use these Wi-Fi signals for localization? And they came up with a system that is called radar. And although radar means something that's very classical, where you want to shine a signal and look at where planes are using radar, this radar is essentially Wi-Fi radar. And the goal was to localize laptops or PDAs. At that time it was called PDAs, or personal digital assistants, in indoor environments. Okay, and they said, look, we cannot do trilateration. So the idea they had was what is called RSSI fingerprinting. Okay, so RSSI is what is called received signal strength index. Okay, this essentially means the power of the signal that is received. Okay, so suppose a Wi-Fi access point is sending a signal to a mobile device, or vice versa, doesn't matter. This signal arrives after many reflections. Right? Now, all these reflected signals, imagine the line of sight signal is like this. The reflected signal will arrive like that. Another reflected signal will arrive like that. Sorry. Another reflected signal will arrive like that. Another reflected signal will arrive like that. Sorry. And so on. So all these reflected signals, which are essentially shifted versions of the signals, right? You see why it is shifted, because when you undergo a reflection, the signal gets delayed and comes later. So all these line of sight signal and the shifted versions of the signal will get added up, and that will create some power of the signal. Right? All these signals get added up. Now, if they all add up on top of each other, the signal will be very high. If they add in a way that they cancel each other, the signal amplitude will be very low. Okay, so it's kind of random, and that's why this addition process is kind of a random process. And sometimes people model the amplitude of the received signal as a random variable. Okay, now this power of the signal is called the RSSI. Guys, let me just quickly mention what the difference between power of a signal and the energy of a signal. Right? The power of a signal is nothing but the average of the square of the samples of the signal. So if you have, so the formula for power is 1 by k sigma I equals 1 to k SI squared. Okay? So SI is the ith sample of a signal. So if you sample this signal, well, actually let me say that the addition of all these, the addition of all these signals, the line of sight plus echo, the addition of all of that gives you this new signal. And if you now sample this signal, let's call that sample SI plus 1, so on. Then the power is essentially the average over the SI square. So you basically take this part and you square it. You also take this part and you square it. I'm assuming that the amplitude is greater than 1. That's why the square becomes greater than the amplitude. If the amplitude is less than 1, the square becomes less. So you square it, and then you take those values, those are the SIs, and the sum of all those SIs divided by k is power. On the other hand, energy is just I equals k SI square. Okay. Basically, you don't need to average it anymore. So that's why energy is monotonically increasing, whereas power is always getting divided. So at infinity, the power is 0 because you've divided by infinity. Great. So RSSI basically is the power that the receiver is receiving at every sample, and Wi-Fi radar is an idea that says, let's use the power of this signal to do localization. And here is the core idea. Okay. Imagine this is the floor of a building, and imagine there's a bunch of Wi-Fi access points. At different places. Okay. So what radar said was, look, actually it has a very trivial idea. Okay. And it's kind of a brute force idea, but it was among the first ideas that brought localization to Wi-Fi. And many technologies that when you look back, right, 20 years back, 30 years back, it'll look trivial. But to be able to stand when people are thinking about Wi-Fi, where people are thinking about sending bits over Wi-Fi and internet connectivity over Wi-Fi, at that point in time, to envision that we can use this for localization was actually exciting, right? So oftentimes it's easy to trivialize certain solutions, think that it's an easy solution, but doing it 20 years back, I think was quite interesting. Okay? So this is what you do. So a person walks on the floor with a laptop. This is what radar actually did. And this person knew exactly where the laptop's location was. Let's call this location L1. And this laptop would send a Wi-Fi signal. Let me draw that in blue. And the signal would go towards all directions, and all the Wi-Fi access points would get the signal. Let's name this Wi-Fi access point as W1, W2, and W3. So now each of the Wi-Fi access points, they will record the RSSI that it received from that beacon from that laptop. Beacon means one signal. So W1 would record this beacon's RSSI as, let's say, S1, what should we call it? RSSI, let's call it R1. W2, let's call it R2. W3, let's call it R3. But because it came from location L1, let's put a subscript over here, which is 1. Sorry, superscript. Okay. Now then what this guy would do is it would go, oh, actually, let me be more precise. Yeah. So now what this guy would do is that he would now rotate the laptop. Initially, the laptop was facing north. Now the laptop faces south. Okay. And again, it would transmit that signal. And now the Wi-Fi access points would again receive it. And initially, let's call it 1, north. And now the receiver would receive R1, 1, south. Right? Location 1, subscript is access point, superscript is the location and the orientation. So let's generalize, write this as general. RSSI at API from location J, orientation. Okay. So now this person would go to many locations, L1, L2, L3, L4, L500. And at each location would do 4 orientations, or how many ever orientations he has the patience for. And he would keep a record. He said, okay, at time 9 o'clock, I was at location L1 and I was facing north. At time 9 o'clock, 30 seconds, I was at location L1 and I was facing south, and so on. And finally, the access points would also record the timing information, and eventually radar created a table. Okay, and the table had the following fields. It would say location, orientation, and RSSI at W1, RSSI at W2, and RSSI at W3. Okay, so this would be like here. Location will be L1, 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 L1. This will be north, south, east, west. And this would be R1, some value, R1, 1N, R1, 1S. And this will have some value, whatever the value that was recorded. R1, 1 east, R1, 1 west, and so on. And then there will be L2, 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 so on. And this will go all the way till L500. Let's say. I don't know how many locations they would go to, but yeah, it will be 500. So this is called calibration, or this is called training. And they would eventually have all this data. And the labels of that data will be the location and the orientation. Okay. Now, imagine once you have done this whole job, now suppose some new guy, some blue guy now comes to this building, to this floor. And this blue guy now stands over here. And now from his laptop, in some orientation, which we do not know, and from some location, which we do not know, that blue guy transmits a beacon, and that signal arrives at all these access points. And let's say now the access points record some value, let's say P1, P2, P3. That's the power received by access point 1, access point 2, access point 3. And the question is, what is this user's location and orientation? Okay. So what do? What you really need to do is you need to take these 3 values and match it and try to see which row matches these 3 values the best. Right? If the red guy who was doing this training or the calibration, or also that's also called fingerprinting. Actually, it's also often called war driving. Let me write out all these names because these are all popular terminology. It's called calibration or fingerprinting or war driving or training. This is the phase where you go around the entire house and collect this data. Okay. So if this red guy during fingerprinting happened to be in the same location as the blue guy, then there's a good chance that corresponding power values that were recorded by these Wi-Fi access points is very similar to P1, P2, P3. Right? So then P1, P2, P3 would exactly match that value, and then you can immediately read out the location and the orientation of the that particular red person's measurement, and you can immediately say, oh, you know, this new guy, this blue guy is actually at this location and this orientation. That's all. So you're basically doing a matching of values. Okay. Now, how do you do this matching? That's really the question, right? This is a vector. These are all vectors. So how do you do the matching? Okay. And this can be nicely modeled again as a vector where you say, look, I have 3 dimensions where dimension 1 is the RSSI at axis point W1. This is RSSI at axis point W2, and this is RSSI at axis point W3. And location L1 and north, that corresponds to 3 values. So the value, so that is essentially a vector, which is location L1 and north. Right? In other words, this value is nothing but R1, 1, comma, n. This value is R1, R2, sorry, R2, 1, comma, n. This value is nothing but R3, 1, comma, n. Right? That's a vector. So now if you erase the vector and if you think of that as a point, that point corresponds to the signal power received by the access points from location L1n. Right? So now imagine those 500 points. So in this 3-dimensional space, those 500 points would be scattered all over the place. Right? I hope you see that. And now when the new guy comes into this building, this blue guy comes into this building, the blue guy comes up with a measurement. The blue guy sends a beacon, the Wi-Fi access points do the measurement, and that is another 3 values, which is this P1, P2, P3. And P1, P2, P3 is also a vector. So let's call it a blue point. And that blue vector happens to be, let's say here, which is this blue point. Let me remove the vector so that we can always think of it as terms of points. And now the question is, now the question is this blue point, what is the corresponding location? And as you can say, it's not very hard to now say which is the location that best matches to the blue point, right? What would you do? And there are very simple answers to this, right? One answer is nearest neighbor. Nearest neighbor essentially says what? Oh, figure out which is the closest red point and declare that red point as the location of the blue guy, blue user, right? So pick nearest trained labeled point and declare the label as the blue user's location. Very good. But you know, that has some problems. Can someone think of a problem? I would like you to pause the video for 5 seconds or 10 seconds and think of what could be the problem with picking the nearest neighbor and declaring that neighbor's label as the problem, as the location. Okay, I hope you've thought of the reason. And the reason is these measurements that you make during the training phase can have all kinds of noise and error, right? Someone else might be transmitting a signal. There can be all kinds of reflection. The value of these signals, these amplitude values, can be random depending on what objects there are in the environment, right? So imagine at some location, the measurements that were made by the Wi-Fi access points were very noisy, which means the closest point that you have to the blue point should have actually been somewhere else. But because of the noise, it happened to be over here. Now, when the blue point picks this closest point, it actually makes a big error in terms of the localization. Right? So nearest neighbor is like very risky. It's very sensitive to noise, right? Outliers, right? So how can you solve it? Again, the answer is not very hard. Think of it for 5 seconds. Just pause the video and think. Okay. The simple answer is, let's, instead of taking the nearest neighbor, let's take the k nearest neighbors and pick and compute the center of gravity. Or actually, let's just call it the average. Let's not give it fancy names. Let's compute the average. So what do I do? Simple. I say, look, let's say k equals 4 or 5. Okay. I pick the five nearest neighbors from blue. Remember, blue is the measurement from the blue user's location. So maybe 1, 2, 3, 4, 5. I take these 5 guys. I take the average of their locations, and that location might be this one, right? Sorry, I shouldn't say that one, because this is the signal space. I take their locations. Let's say this was L5, this was L7, this was L6, this was L33, this was L54. So I take those locations, I take an average of those locations, I take an average of their orientations, and I declare the average as the blue user's location. Okay, that is more robust, because even if this location was erroneous, this measurement was erroneous from location L5, suppose this location was actually over here, but at least these other four locations hopefully were not also bad. And therefore, even though this error is high, these errors are small. So on average, your error becomes smaller. One question I want you to think is, will k nearest neighbor always perform better than nearest neighbor? Okay. I want you to think about this question, and we'll talk about it on Wednesday. And I'll just quickly write this question. Can you find a scenario in which k nearest neighbor, this is called KNN, is or performs worse than nearest neighbor? Okay, I want you to think about it, because this will help you understand what is going on. And the final comment I want to make about Wi-Fi localization is the following. How do you pick N? How do you pick K? Right? If you pick K as 1, you're very sensitive to noise. So why not pick K as 100? What's the problem? Think about what the problem is. If you pick K as 100, for example, if you pick K as 500, and let's say there are 500 measurements, then whatever the blue point, wherever the blue point is, the answer will be the same, right? because you'll take all the 500 points and you'll take the average of those 500 points. So that means as you increase K, your spatial resolution becomes coarse-grained, becomes worse, it becomes more granular, right? But you're more robust to noise. As you reduce K, you have fine spatial resolution, but you become sensitive to noise and outliers in those power measurements. So how do you pick K, right? There's a trade-off over here. And there's no silver bullet, there's no provably the right way, but one nice heuristic that people use is the following. They take those 500 points and they take only 400 points out of them, and the remaining 100 points, they use that for testing. And they create this three-dimensional training phase with only 400 measurements. And the remaining 100 are like test points. Okay? And with these remaining test points, 100 test points, they basically look at what the performance is for different values of K. So you start with K equals 1, K equals 2, K equals 3, so on, till K equals maybe 50. Right? I mean, beyond that, it's not reasonable. And for every K, for all those 100 points, you figure out what the accuracy is, and you draw maybe the average accuracy, average location accuracy over all test cases. And the hope is you should see that the curve, the accuracy, okay, so let's call it the average error. Average location error. So average location error, what should it look like? At 1, the error actually should be higher. As you increase K, the error should decrease, and then the error should increase again. Right? And then you basically pick the minimum of this, and whatever K that corresponds to, that is called K star, or the optimal K. It's a heuristic, it's empirically done, but this is a way where from the data, you're basically pulling out the parameter of your algorithm for K nearest neighbor, and then you use this K star for the new guys, for the blue points that are coming in. Remember, these 100 test cases are still the 100 red test cases out of 500 red measurements. This gives you K star, and then you use the K star, use K star for new test cases, new blue test cases. Okay? For these 100 red cases, you can measure the error because you actually know the truth. You actually know the ground truth locations for those 100 cases. As a result, you can measure their error, and then you use that for the blue test cases, and that is the system that is running. And radar was initially developed by Microsoft Research, and Microsoft Research ran this algorithm on their floor. This was back in 2000. And the results, the Wi-Fi based localization results, looked something like, it varied from some 2 meters in the best case, that was when things were lucky, right, all the way to 10 meters and more. It was a distribution. But around the average, I think if I remember this properly, the average was 5 meter accuracy, but there was quite a long tail. That means there were lots of cases where there were 20 meters error, 10 meters error, and so forth. But the performance is not that important over here. What is really important is this was kind of an initial way in which Wi-Fi power, you didn't have to do triangulation. You do not have to figure out what the echoes look like. The real idea was that just using this simple idea of Wi-Fi power, you need not know the Wi-Fi access points, locations. You need not know anything. you have to, of course, do this brute force training phase. But once you do that, after that, you use that database or this three-dimensional signal space to actually localize the mobile device, the laptop, right? And of course, the more the access points, if you have, instead of 1, 2, 3, if you have 10 access points, then your performance becomes better and better, simply because you have 10-dimensional space and their matching becomes stronger. So that's basically the idea of Wi-Fi radar. One of your programming assignments that's coming up will actually make you do localization using RSSI from real data, from real Wi-Fi access points. So there you'll get to play with Wi-Fi signals and do localization using KNN and maybe pick the best K. Okay, that's the end of this lecture. Now, the next thing we are going to talk about in part B of the video is why is the accuracy with Wi-Fi localization high? Why is it not centimeters? Why is it not really very accurate? Why do I have to go all the way why do I have 10 meters of error? Okay. And that goes back to this notion that Wi-Fi signals have these echoes, and these echoes make these power measurements erroneous. But instead of these complete RSSI measurement, if you could somehow figure out the power of only the line of sight path, then that would be very useful, because then the accuracy can become much better. If you could only figure out how the signal arrived, or what was the power of the signal that arrived along the straight line from the transmitter to the receiver. So in the next, the second part of this video, we are going to talk about the wireless channel. We need to understand what we mean by wireless channel, and we need to understand a little bit more about this multipath and model this wireless channel. And once we understand that, we are going to get into a little bit more depth around how to actually utilize the channel and do more interesting things with Wi-Fi localization. One of those ideas would be triangulation. Okay, but before we go to triangulation, in the second part of the video, we will talk about Wi-Fi channel and multipath and convolution. So stay tuned for that. Start the next video. Okay, thanks.